Hello students, welcome to AskPrep. My name is Kaganavi. In today's class, we'll continue about the periodic properties and classification of the elements. So in the previous class, we studied about radius of a cation. Now, we'll continue with the radius of anion. Radius of anion is bigger than the corresponding atom, maybe cation. So here an example is chlorine. The number of electrons here is 17. The number of protons is also 17. So the reason why it is a big, because of the large size of the anode, more number of valence shells are present, and the effective nuclear charge decreases in the formation of anion. So what happens? The electrostatic force of attraction between the nucleus and the outer electrons decreases. As a result, the size of the anion increases. And also due to interelectronic repulsion increases due to the expansion of the electron cloud, it takes place. So the next concept is about isoelectronic species. So what is an isoelectronic species? It is a series of atoms, ions or molecules in which each species contains same number of electrons but different nuclear charge is called the isoelectronic species. Here in N3 molecule, the number of electron is 10 and the number of proton is 7. In O2 minus molecule, the number of electron is 10 and the number of proton is 8. In F minus, the number of electron is 10, proton is 9. In neon, Ne, it is 10 and 10. In sodium ion, Na plus, it is 10 and 11. In Mg2 plus, it is 10 and 12. So you can see here, all the elements consist of same number of electrons, but there is a variation in the number of protons. In isoelectronic series, atomic radii decreases. As a result, nuclear charge increases and the number of electrons are same and the number of protons is increasing. So, the effective nuclear charge is also increasing and the decrease in the atomic size. So, if the effective nuclear charge increases, atomic size decreases. In isoelectronic series, atomic size decreases with the increase of effective nuclear charge. So these are some of the example of isoelectronic series, that is S2 minus Cl minus K plus A2 plus Se3 plus. So it continues with the order. So the next concept is about periodicity in atomic radius and ionic radius. So in a period, what happens from left to right? Effective nuclear charge increases as the next electron fills in the same shell. So what happens? The size of the atom decreases. So in a group from top to bottom, the number of shells increases. So the atomic size also increases. So if the nuclear charge increases but its effect is negligible with increasing number of shells, the atomic radius of inert gas is shown larger in the period because of its van der Waals radius, which is larger than the covalent radius. And here the van der Waals radius of inert gas increases from top to bottom in a group. And for transition elements, there are 4 series: 3D, 4D, 5D and 6D. 3D series is from scandium to zinc, and 4D is yttrium to cadmium, 5D lanthanum and hafnium to Hg, mercury, 6D actinium to Rf up to its complete elements also. Here, the periodicity, the atomic size first decreases due to the increase in the effective nuclear charge, and then it becomes constant and again it increases. In the transition elements, electrons are filled in the n-1d orbitals. So these n-1d electrons, it starts to screen the ns electrons from the nucleus. So the force of attraction between the ns electrons and the nucleus decreases. So this effect of n-1d electrons over ns electrons is called shielding effect or screening effect. Here, the atomic size increases due to shielding effect and it balances the decrease in the size, and almost the size remains the same up to 80% of the nuclear charge. So, moving left to right, so there is a very small decrease in size and it is considered the size almost the same. In the first transition series, what happens from scandium, the atomic size slightly decreases from scandium to manganese due to the effective nuclear charge is stronger than the shielding effect. And the atomic size from Fe to nickel almost remains the same because both these effects balance each other, the shielding effect and the effective nuclear charge. And the atomic size from copper to zinc slightly increases because shielding effect is more than the effective nuclear charge in copper and zinc. Inner transition elements. So if we move along the lanthanide series, there is decrease in the atomic radius as well as the ionic radius, and the decrease in size is regular in ions but not so regular in atoms. So this is called lanthanide contraction. There are two peaks at both the EU and YB elements. So this is due to the metallic bonding. As they form metallic bond, two electrons from each contribute in the bond formation, which in turn leads to the half-filled and completely filled 4f orbitals. So the next concept here is about lanthanide contraction. In lanthanides, the addition electrons enters the n-2 f orbital. The mutual shielding effect of n-2 f electron is very little because the shape of the f subshell is very much diffused. So in the sense, the shape of the F shell is not so much correct or is not proper. So the electrons are very little present and the effective nuclear charge increases and the mutual shielding effect also increases of n-2 f electrons. And here in case the outer electrons are more attracted by the nucleus. As a result, the atomic and ionic radii decreases from lanthanide to ruthenium. So this type of contraction also occurs in actinides, and this jump in the contraction between the consecutive elements in the actinides is greater than lanthanides. This is why, due to the shielding of 5f electrons, which are therefore pulled more strongly towards the nucleus. So in the group, atomic radius of elements increases, moving from first transition series to second transition series from 3D to 4D. So this is due to the increase in the number of shells with increase in the atomic number. The atomic radii of second and third transition series in a group is almost the same except in yttrium and lanthanum. In third transition series, there are 4 lanthanides in between La and 3b of and HF of 4b groups. The atomic radius of hoslium decreases due to lanthanide contractions. And the difference in the nuclear charge in the elements of a group in the first and second transition series is plus 18 units, while difference in the second transition is 32. So due to increase in the plus 32 units in the nuclear charge, there is a decrease in the atomic radius which balances the increase in size due to increase in the number of subshells. So in moving in a group from second to third transition series, so the atomic radii almost remains the same and the difference is around 0.02 angstrom. So the next is ionization potential. So this is the amount of energy which is required to remove the almost loosely bound electron from the outermost shell or from 1 mole of an isolated gaseous atom of an element in its ground state to produce a cation is known as the ionization energy. Ionization energy is generally expressed in electron volts, so it is also known as ionization potential. So the energy required for the removal of first, second and the third electron from the gaseous atom is called the respective ionization energies. And the order is given as IE1 less than IE2 less than IE3. So this is why, because second and the third electron removal from the unipositive and dipositive cations. So as a result, the effective nuclear charge increases with the increase of the positive charge. And hence, the attraction between the nucleus and the outermost electron increases and more energy is required for the removal of the electron. So then what are the factors which affect the ionization potential? Atomic radius. The value of ionization potential of an element decreases as its atomic radius increases. This is due to the electrostatic force of attraction between the nucleus and the outermost electron decreases as the distance increases. So, the energy which is required for the removal of electron is comparatively low than the ionization potential decreases. So, effective nuclear charge. So, if the effective nuclear charge on the nucleus is more, then it will be very difficult to remove the electron from an atom because of the electrostatic force of attraction between the nucleus and the outermost electron increases. So, greater energy will be required to remove the electron. So, the next concept is about penetration effect. So, this penetration effect is the order of the energy which is required to remove the electron from s, p, d and f orbitals of a shell. So, because of the distance of the electron from the subshell increases as the size of the shell increases. The value of ionization potential of beryllium is for beryllium and magnesium are more than the ionization potential of boron and aluminium. Why? Because of the penetration power of 2s and 3s electrons is more than 2p and 3p electrons respectively. As a result, more energy is required to remove the electron from 2s and 3s orbitals as they are very close to the nucleus and are tightly held. Shielding or screening effect. So this is the effect which increases if the number of electrons in the inner shell between the nucleus and the outermost electrons increases. So this results in the decrease of the force of attraction between the nucleus and the outermost electron, and lesser energy is required for separation. As a result, the value of ionization potential decreases. Stability of half-filled and fully filled orbitals. See, according to Hund's rule, the stability of half-filled and completely filled degenerate orbitals is very high. So, more energy is required to separate the electron from the atoms having half-filled or full-filled electronic configuration. For example, removal of electron is comparatively difficult from the half-filled configuration of nitrogen as compared to the full-filled configuration of any other atom. And the ionization potential of inert gas is high due to stable electronic configuration. Periodicity. So here in ionization potential, from moving from left to right, the ionization potential increases due to the effective nuclear charge increases. So there is an exception. In a period, the ionization energy of 2a group elements is more than the elements of 3a group because of the penetration power of s electron is more than that of p electron. So the value of ionization energy of beryllium is more than that of boron because the penetration power of 2s electrons of beryllium is more than the 2px electrons of boron. And moreover, here the electrons are paired, that is completely filled as subshells are present. So the ionization energy of 5a elements is more than the elements of 6a because of the half-filled configuration of the P3 configuration of 5a elements, and they are highly stable because of the half-filled. So the 6a groups have the tendency to acquire comparatively more stable configuration. So by the loss of one electron, or ionization energy of nitrogen is greater than oxygen. So for down the group, it decreases, ionization potential value decreases as the atomic size increases. So in a group, what happens as the atomic number increases, the effective nuclear charge also increases, hence the ionization potential increases. The shielding at the top n-1 d electrons over ns electrons increases with the addition of electrons in n-1 d orbitals, hence ionization potential decreases. So if the value of ionization potential is increased due to effective nuclear charge, it is almost balanced. So the decreasing value of the ionization potential increases the shielding effect. So this is due to the small increase of the ionization potential. So in the transition series also, ionization potential increases due to the increase in the effective nuclear charge is more than the shielding effect. And the ionization values of iron, cobalt, nickel and copper are almost the same. So due to the n-1 d10 ns2 configuration of fully filled in zinc element, the configuration is completely filled. As a result, the ionization potential value increases. So in a group, from moving from first to second transition series, the values of IP decreases because of the atomic size increases. So if you move from second to third transition series, the value of IP somewhat increases except the third group, and this is of the 14 electrons are filled in 4f orbitals of lanthanides and which do not sheet the 5d electrons effectively. So thus the increase in plus 32 units in the nuclear charge results in the increase of IP value. So on moving from left to right, this effect increases and it is negligible. So applications of ionization potential. So metallic or electropositive character of elements increases as the value of ionization potential decreases. So in a group, from moving from top to bottom, metallic or electropositive character increases because IP value decreases. So in a period, left to right, the values of IP increases. So metallic or electropositive character decreases. As a result, non-metallic character increases. So if the metal reactivity increases, then the decrease in the IP values is seen. And the IP values of 1A and 2A metals are very low. So they are comparatively more reactive. The IP values of inert gas are very high and they are inactive. The reducing power of elements increases as the value of IP decreases because of their tendency to lose the electron increases. The reducing power increases going from down the group as the IP value decreases. Lithium is an exception, and the reducing power of quantum elements is in the order lithium, cesium, rubidium, potassium and sodium. So the next is determination of oxidation state or valency of an element. If the difference is between the two ionization potential elements is 16 electron volt or more, the lower the oxidation state is stable. So in sodium is the ionization potential value is 42.4 electron volt. This is more than 16 volt. So Na will be stable. Na plus ion will be stable. So whereas the neutral Na atom has a stable electronic configuration of completely filled. So the Ia first 8 groups form the unipositive ions. So if the ionization potential values is 11 or less, the oxidation state is stable. So magnesium is 7.4. So Mg2 plus will be stable. So it forms dipositive ions. So for the third one, if it is 12.8 volt, which is more than the 11 electron volt, then aluminium must be stable, that is Al plus, due to the lattice energy distribution and the difference of second and third IP values. And this relation of diagonal relationship in the periodic table is explained with the help of lithium and beryllium, which are more similar with the second element of the second group of magnesium and aluminium, and they resemble the similar physical and chemical properties. So the next one is electron affinity. The amount of energy released when an electron is added to the outermost shell of 1 mole of an isolated gaseous atom in its lowest energy state is called the electron affinity. So then what are the factors affecting the magnitude of electron affinity? atomic size. So in general, if the electron affinity value decreases with the increasing atomic radius because of the electrostatic force of attraction decreases between the electron which is being added, and the atomic nucleus also increases due to the distance between them. So electron affinity is inversely proportional to the atomic size. So the next is effective nuclear charge. So electron affinity value of the element increase as the effective nuclear charge on the atomic nucleus increases because of the electrostatic force of attraction between the electrons which is being added, and the nucleus increases. So the amount of energy released is also more as the electrostatic force of attraction increases. Electron affinity with respect to the effective nuclear charge. Screening or shielding effect. Electron affinity value of the element decreases with the increasing shielding or screening effect. The shielding effect between the outer electrons and the nucleus increases as the number of electrons increases in the inner shell. So electron affinity is inversely proportional to the shielding effect. Stability of half-filled and completely filled orbitals. So the stability of half-filled and completely filled degenerate orbitals of a subshell is more, and so it is difficult to add the electron in such orbitals, and lesser energy is released on addition of an electron. Hence, the electron affinity value decreases. So then what are the exceptions here? The electron affinity values for alkaline earth metals is 0 except beryllium and magnesium. Of alkali metals is also 0 because of the tendency to lose electrons instead of gaining the electron. And the electron affinity values of nitrogen, phosphorus are lesser than the electron affinity values of carbon and silicon due to the half-filled configuration, and of nitrogen and phosphorus is more than the full-filled configuration of completely filled in carbon and silicon. And the theoretical value of the electron affinity of zero group inert gas elements is 0 due to the stable S2P6 configuration. So in a group, from moving top to bottom, the electron affinity value of elements decreases because of the atomic size increases. And the electron affinity of fluorine is less than the electron affinity of chlorine. So that 2p orbitals in fluorine are more compactly arranged to the nucleus or held to the nucleus compared to the 3p orbitals of chlorine. So the electron which is being added to the orbitals, it experiences more repulsion and the electron affinity value decreases. So the next is about electronegativity. So electronegativity, it is defined as the tendency of an atom to attract the shared pair of electrons towards itself in a covalently bonded molecule. So higher the ionization potential and higher electronegative values, which implies the higher electronegative value. So this, to give the electronegative values, there are few scales proposed by Pauling and Mulliken. Electronegativity is the tendency of an atom to attract the shared pair electrons towards itself. So Pauling scale, Pauling related the resonance energy of a molecule with the electronegativity of the atom, and he named as Xa and Xp are the electronegativities of atoms A and B respectively. So here is the value given by him. This is the experimental and theoretical value. So he assumed the electronegativity value and calculated the values of the elements from the above data given below. So the next one is Mulliken's electronegativity. So according to Mulliken, the electronegativity of an element is the average of its ionization potential and electron affinity. So Mulliken's electronegativity, that is Xm minus 0.615 or Xp is equals to 0.336 Xm minus 0.2. Here Mulliken's values are 2.8 times greater than that of Pauling value. So ZEF is equals to Z minus sigma. So Z is the number of charge present on the nucleus or the number of protons, and the sigma is called the shield constant. Factors affecting the magnitude of electronegativity. Atomic radius. As the atomic radius of the element increases, the electronegativity value decreases. The electronegativity value in the effective nuclear charge on the atomic nucleus increases. So if the oxidation state also increases, then the electronegative value also increases. So hybridization. So s electrons have more penetration effect. As a result, s orbitals have more effective nuclear charge. So we can see here in s character, in sp3 hybridization, s character is 25%. In sp2 it is 33.3%. In sp it is 50%, and the electronegative value is more in case of the more s character hybridization. If the s character is increasing, electronegative value is also increasing. So the next is periodicity in electronegativity. So in a period, if we move from left to right, the electronegativity increases due to increase in the effective nuclear charge. In a period, the electronegativity value of first A alkali metal is minimum and that of 7A group halogen is maximum. So in a group moving from top to bottom, the electronegativity value decreases because of the atomic radius increases. And the electronegativity value of fluorine is maximum and that of cesium is minimum. And here the cesium and francium is less, the electronegativity, due to the increase in the plus 32 units of the nuclear charge, and this in turn increases the effective nuclear charge. On moving from second to third transition series in a group, electronegativity increases due to increase of plus 32 units. And the electronegativity of inert gas elements is 0 due to the stable NH2NP6 configuration. These inert gas are monoatomic molecules, and the electronegativity is the property of these bonded atoms. Applications of electronegativity. So here it is due to the partial ionic character in covalent bond. The ionic character of a covalent bond increases as the electronegativity difference of the bonded atoms increases. So the order of the ionic character in HX bond is as follows, that is HF is greater than HCl, greater than HBr is greater than HI due to the electronegative values and their S characters, which are the number of shells decreases in the fluorine and all. So what happens, it is morely attracted to the nucleus. Bond strength also plays an important role in electronegativity. Due to the difference in the covalently bonded atoms, delta X increases, and this is the electronegativity value. The bond energy of the covalent bond also increases. So, for example, the order of HX bond strength is HF greater than HCl, greater than HBr, greater than HI. So, if the bond strength is decreasing, the acid strength is increasing. So, the order of increasing acid strength is HF greater than HCl, is less than HBr, is less than HI. Acidic and basic nature of oxides. The acidic nature is increasing as they move from left to right. So in a period also from left to right, the electronegativity of the elements increases. So as a result, the difference of the electronegativities of oxygen and the elements decreases. If the XO and the XE values is about 2.3 or more, the oxide will be basic. Oxygen and the other elements. If the value is less than 2.3, the oxide will be acidic. So the oxides of 3A elements are amphoteric. And the order of acidic or basic nature of the oxides of third period elements may be given as Na2O, MgO, SiO2, P2O5, SO3, ClO5, and the basic nature is decreasing, acidic nature is increasing. So the next is metallic and non-metallic properties of elements. So the metallic character decreases as the electronegativity increases, and moving from left to right in a period, the electronegativity value of the elements also increases. As a result, the metallic character decreases. So in down the group, the electronegativity decreases and the metallic character increases. It is the vice versa. So thank you students for watching, and I think you got this concept today. If you have any doubts, feel free to ask or message us